that. So I want to talk about a couple of things. I did grade your lab, your Ohm's Law lab, so I just have some comments that I wrote down. And typically when folks turn in the lab, I tend to look at things that might need to be worked on. So first of all, and this is not something we have to work on, but I'm doing something different this semester. Because I'm grading online and using Canvas to grade is very slow, so I created a code, a grading code, and I emailed you the grading code. And so instead of me writing words like sig figs or units, although in some cases I did write units, I'm just going to put a number down and then tell you the amount of the point deduction. Okay, that way I can grade faster, because otherwise writing in Canvas is very slow and cumbersome. Okay, so if you don't understand some of the numbers numbers you see on there, just look at the code that I sent you. And so I'm going to use that from now on. Really, you only have 3 more lab write-ups this semester. Okay, I'm sorry. After today, you only have 2 more lab write-ups this semester. All right? So I'm going to use the grading code. Now, a number of you, I think, maybe don't remember what it means when it says plot voltage versus current. Maybe you don't remember what that means. Okay. Plot Y versus X. This is the dependent. Actually, in their case, it really isn't, but I shouldn't say that. And the reason why we plotted Y versus voltage versus current, the slope directly gives you the resistance. Okay, so you want to have delta V here and I here. Really, I should say potential difference versus current, but anyway. So the slope of that graph is going to give you the resistance. A lot of folks plotted I versus V. They did it backwards. And they did take off a point, and the reason being is that the analysis people did was getting the information from that was incorrect. So you do get a graph, you get a slope, but the resistance here is 1 over the slope. So most people, when they measured the resistance, they got a value of less than 1,000 ohms. But when you plot it backwards, your resistance is over 1,000 ohms. That's I can tell. I mean, all I had to do is look at the value that you got without looking in the graph. I could tell you plotted it backwards. All those resistors, the resistance was a little bit less than 1,000 ohms. But you can still determine the resistance and its uncertainty from this graph. But I think maybe I had 1 or 2 people actually do this part correctly, but then they incorrectly calculated the uncertainty. So if I plotted this and I wanted to calculate delta R, so I want to know R plus or minus delta R. So let's say I got the slope was equal to 1.04 plus or minus 0.05 per kilo ohm, because that's the units of this. How do I get the uncertainty of my resistance? You tell me, how should I get the uncertainty? How do I get delta R from here? Obviously, R is 1 over the slope. That's fine. Okay, so R is 1 over the slope. But what is delta R. Based on this calculation, how do I do it? What's the process for error propagation? All right? What is the process for error propagation? If R is 1 over the slope, I'll write it as 1 over m, then delta R is the partial of R with respect to the slope times delta slope. Or let me write it this way, the derivative of R with respect to m, delta m. If you do this, you will get 1 over m squared delta m. And I want the absolute value of this thing. That's the correct way of calculating the uncertainty. And I don't think anybody did that correctly for the students who flipped the graph, who plotted the graph wrong. So that's not correct when you're doing the analysis. Okay, am I clear on that? Because that's important, okay? You flip the graph around and you want to get the right results, you have to do the analysis correctly. And so the reason really I took the point off for graphing it backwards is because you didn't do the analysis correctly. Something wasn't done, at least one thing wasn't done correctly, okay? If you have a graph that's linear, you should never choose this as a function for graph. Why? Why should you never use this? Anybody? Yeah, that means you're forcing the graph to go through the origin if you do this. You might have a y-intercept just because of maybe an issue with calibration. So never, ever use this for a linear graph. Always use y equals mx plus b. Okay. Now, a number of you was able to get the new version of graphical analysis for free from Graphical Analysis. There's a problem with the software, and there's a big problem with that software. Okay? It doesn't show the uncertainty in your curve fits. I need to see them. So yeah, you may use Graphical Analysis, the new version from their website, but their new software does not show the uncertainty in the curve fit. Because everybody who used the new version, because I can tell from the graph, everybody who used the new version of the Graphical Analysis software, they didn't quote the uncertainty in the curve fit. So don't use the new version of graphical analysis, because I need to see the uncertainty. We're doing error analysis in this class, so it's not going to be of any use to you if the software doesn't do any error analysis in its curve fit. Okay. And so make sure that you show your uncertainties in your curve fit results. Okay, when you have your graph, and I talked about it, these labels have to be there. Don't just leave it Y here and X here, which some people did. tell me what they are with units, put a title on here. Okay. Oh yeah, by the way, so I'm a little bit older than you folks. Yeah, you know, the RMSE is, well, the uncertainty in what, I guess, Patrick? The uncertainty in which value? It just tells you how good the fit is. But it doesn't tell you the uncertainty in the slope. And it doesn't tell you the uncertainty in the y-intercept. That's what we're looking for. But you're right, it tells you how good it does tell you how good the fit is. But I need to know how well you know the slope and how well you know the y-intercept. Because those are the values we're going to be using to calculate things. We don't do anything with the RMSE in subsequent calculations. We use it as a tool to see how good the fit is. I mean, it tells on uncertainty, but just in terms of how good the overall graph is. Okay. All right. Yeah, so like I said, I'm a little bit older. And so if you do this, can you see the X and the Y on that graph? Yeah, so I can't see it when you on the screen. I don't want to have to magnify the screen every single time. Just make the font a little bit bigger. Don't make it gargantuan, but make it big enough so a person can read it. The font in the graph should be the same size as the type, the font type in your document. Okay, the font size in your graph should be at least the same size as the font in your document. So don't make it teeny weeny. And some people did this, Here's sheet. All right, let me redraw. Let me erase the board. I'm writing too much stuff here. Here's your sheet of paper, and your graph is like this. You're not printing this out, so you don't have to worry about saving paper. Make your graph a nice size. Although the people who didn't make the graph real small, they did make the font big, okay? But still, you should make it take some space on your page, okay? Because we're not going to print it out. Just make it easy for the reader to see, okay? So, when you're answering questions, and I tell this to my Physics A class. In fact, I tell it every class I teach, every lab I teach. You'll be asked a question. You might have to make a judgment, but your judgments are based on evidence. So when you answer a question, you say, "I believe." Or "I feel," or "in my opinion." You don't want to really say that. All right, this is a science class. We're not doing a political discourse. So what you want to say is, the data indicates that, or the data shows that. You want to start like that. Or based on the evidence, we can say that. So your judgment, whatever judgment you're making, is based on the evidence. So you want to start off with that. If you say "I believe it," the reader will think, are you commenting based on evidence or not? Okay. And I say this nowadays because everything nowadays is so politicized. I kind of want you guys to focus on making comments based on evidence. These terms make it look like you're doing some sort of political discourse. Okay, because judges, even Supreme Court justices, they render an opinion. Okay, we try to do as best we can. We try to do things based on evidence as best we can. Okay, so you should try to avoid answering questions starting with these phrases. There's others. You don't want it to sound like you're answering based on a belief, but you want to answer based on evidence, okay, or on data. And then granted, this is hard we're so used to doing this, it's hard to get away from it, okay. So one of the things I've noticed in discussing things with students, the multimeter, and I think this is why these are not very expensive multimeters, the precision, the displayed precision of the multimeter is really greater than the accuracy of the multimeter itself. The multimeters that we use on campus are not like that. If you look at the manual, it'll tell you exactly what the uncertainty is. So if you measure resistance, let's say you measure 100 ohms, and you do it on the 200 scale, the manual will tell you that the accuracy of this is 0.4% plus or minus 5. This tells you the least significant digit is off by 5. So this would be, the uncertainty would be, of this would be 0.4. Okay, so the least significant digit is off by 0.5. So this would be, actually it's the one after that, sorry. The value after, so it's going to be, this value. It's not the least significant figure, but the one after. Okay, but we're going to round this off always to 0.4 anyway. We're always going to round it off to least significant figures. So if you go by the manual, I would just quote the uncertainty as 0.4. Okay. And I think what we might have to do for the last two labs, when we want to quote the uncertainty, just go by what we should just go by what the manual tells us. Because you'll actually have more precision. It displays a higher degree of precision than it is accurate, which is kind of weird. At least for this meter, since they know that they should have displayed less digits, or they should have made the meter better. Okay. Any questions on this? Any questions about the grading? Please email me, okay? One of the things I did was I made these labs, usually my labs are worth 20 points, so I made them worth 40 points. So if I find something wrong, I can take a little bit off without really affecting the grade a lot, just to let you know that this is not something you want to do in a lab report. Okay. All right. So I want to talk about our next lab. Our next lab is a project, although it's really worth 40 points like the other labs. And you're going to be building a motor. Sorry, the screen went blank. That's not what I want. Sorry. Hold on a second. Okay. So you're going to build an electric motor. And you have until November 25th to build this motor. Okay. You have a kit that came with your, or a motor kit that came with your lab kit. So hold on a second, let me switch views. Looks like this. This is your motor kit. In it, you have the base made out of wood. You have, this is the most expensive part, the magnet wire. Okay, let me change the view again, sorry. You have magnet wire. This is expensive. This is, by the way, this has an enamel coating on it. Okay. You want to be careful with this. Then you have a bunch of nails. And you should have a compass too. You have a bunch of different size nails. And you're going to use this, the nails, to build the armature and the electromagnet itself. And you have instructions for how to build it. Okay, so everything is there that you need to be able to build a motor. We did talk about the electric motor last week. And so this is basically you applying the ideas involving the motor. So let me show you, I'm going to switch cameras. Let me show you what the motor will look like. And as I switch cameras, I'm also switching my microphone, so the sound will probably not be as good. Okay, let me get one of the motors. This way I can give you a closer view. So this is one of the motors that a student built. And I'm going to cover up the name. And this student's motor actually ran on 1.12 volts. Now, of course, when students built this motor, they were on campus, so we can actually use a power supply to test it and improve it as needed. We're just making one with a commutator. So, Patrick, yeah, I don't. I'm not too familiar with their version of their motor project. This is a very simple one with the commutator. So let me show you the armature. This is the armature looks like. Okay, and then here's the commutator. If you can see it. What this student did was they bought some copper sheet, and you use a copper sheet to make the commutator, which gives you better contacts. Now, in the instructions, what they do is they actually tell you to just bend the wire to create the commutator. It'll work. It probably won't work as good as this. So you have the option of actually using this. Yeah, if you have copper tape, you can use copper tape. And this is essentially what this is. Okay? So you can use copper tape, and you'll get actually better contact. Okay? Now you can always go to Home Depot or Lowe's to get that. There are some rules for this motor, right? So here's your armature. And you're going to wind all that coil. You got to be careful when you do this. So the minimum number of nails in the armature is 2, or you can use a 1/4-inch dowel. So let me switch views again. Let me go to the end of this document. And the rules are there. So the armature must consist of no less than 2.5-inch nails, or a rod or dowel. But you're still going to need the nails because you need something magnetic. Okay. You can wrap. You can tie the nails to a dowel if you want to. Okay. You are allowed to use bearings. So the other example I have uses bearings. Although the example I have didn't work as well. So let me. So you're allowed to use bearings. You need to use the enamel gauge wire that was provided. And then the big one is the armature and the electromagnet have to be connected in series. Okay. So let me switch cameras again. So this one has, student used the bearing, although this one didn't work very well. Okay, the design looks nice, but the students used bearings here and here. I mean, this magnet is beautifully wrapped, so I'm not sure what the issue was. And it's possible that there was too much weight on this. So the magnet was very nicely wrapped, but the coil was not. You actually want this to be very nicely wrapped. This one's not as important, but you want this to be very nicely wrapped because you want that thing to turn very easily. You want the moment of inertia of the armature to be as low as possible. So you want to distribute the mass as uniformly as possible. So really this one is a better armature. The more uniformly you distribute the mass, the easier it is going to be for this thing to rotate. Okay. You actually want to build this first. You can actually do this while you're watching TV or something, building this. Okay. Building the motor is actually not hard. Making it work is the hard part. Troubleshooting it is the hard part. Because what you need to do is you need to, if you want to get the A on this project, you need to get this thing to run on 3 volts or less, which is basically the 2 batteries we supplied, the 2 D cell batteries. Okay. And last semester when we did this, a lot of people got it to run on 3 volts or less. So it shouldn't be that big a problem. You got to remember that you have to hook up everything in series, not parallel. If you run everything in parallel, you're gonna use too much current, and you're probably melting enamel coating. And then you're gonna have to rewind your wire. So you probably want to get started on this early. Like I said, this is not going to take long to put together. The hard part is troubleshooting. Troubleshooting is an important skill you need to have. I don't care what field you're in. I don't care if you're going to be an engineer, a chemist, or a computer scientist. In any of those fields, you have to troubleshoot. If you're a computer scientist and you write code, you have to troubleshoot your code. You have to figure out what's wrong. You have to develop a process, or you have to learn how to develop processes to troubleshoot something. Good question. What is the highest voltage we can safely test with it? I forget. I mean, I've actually gone up to 11 volts with a power supply on campus, but then I do it for a very short period of time. Okay. Probably 9 volts is probably the highest. I would try. Now, don't use. Now, if you have a power supply, that's even better. But your power supply has to be able to supply a lot of current, like 8 or 9 amps or 10 amps. If you have a power supply that only supplies milliamps, it's not going to help you. Okay. You need a pretty hefty power supply. So on campus, usually we bring out the 5 amp is probably usable. but then you're going to be limited in terms of voltage. You're probably not going to go up to 9 volts. Okay. But 5 amps is probably good. In fact, what you can do then with that is that makes it more of a challenge to really design it better so that you don't have to run it at as high a voltage as you need to. And that's going to force you, I'm hoping, to build a better motor. Okay. So some of the key, one of the big keys, there's really a couple of big keys. And I created a discussion board from last semester. So you can add to it. If you have questions, please ask on the discussion board and I can supply the answers. But I have a list of things you should check for. Like number 1, you have to wrap this symmetrically. You want to minimize the moment of inertia. Number 2, really, and this might be the biggest issue to getting it to really just work, is you need to make sure you have a really good consistent contact between the armature and the brushes. Now this student, this thing kind of fell apart. This student's brushes were made out of stiff wire. I'm trying to cover the student's name. But these are the brushes for this student, and these are made out of stiff wire. Okay, and those are probably better than using the wires we provided. Although these don't bend very well, whereas the ones we provided do. So the biggest issue is making sure you have good contact. And you can test that by measuring the current when you connect it to the power supply. And you can just connect it to the power supply, measure the current, and just slowly spin the armature. If the current varies a lot, that means you're probably losing contact somewhere as it's rotating. Which would mean then you actually have to supply a larger voltage so that it keeps running consistently. Okay, so that's the biggest issue. The second biggest issue is probably how the mass is distributed about the axis of rotation. Those are some big ones. Now, one of the things about this is when you wrap this, you're going to wrap 2 layers. It's around 400, I'm guessing 400 turns, I'm guessing. I know that they say 400 turns on the electromagnet. But when you wrap this and your second layer runs the current in the opposite direction of the first layer, what's going to happen? If you have 2 layers of current in opposite direction, what's going to happen? I mean, your torque is going to be 0. Okay, so you got to make sure when you wrap the second layer, the current is going in the same direction as in the first layer. Because otherwise you're going to get 0 torque. That ain't going to spin. Okay? So wrapping it, the way you wrap it is important. We provided a compass so that you can see if it's working. When you connect it together, you bring the compass near it, the compass should change directions. So that tells you have a magnetic field. You want to test the magnetic field in the electromagnet. Okay, this is the electromagnet. And you want to test the magnetic field in the armature. Do you have questions so far? I will say that the engineering folks and love this lab. They some of them go all out on this lab, which is fine. You can. Okay. I'm hoping that this would be a fun experience for you, for most of you. And folks, and I know some of you are not going to be engineers, and you might see this as a pain, but it's actually not that hard to build and make it work. It might be a little bit harder to run it at 3 volts. Now, if we were on ground to get an A, you would have to run it at 2 volts. Yeah, that's the only part is the troubleshooting is always stressful, but then when you get it to work, it feels good. That's typically what happens. The troubleshooting part, I don't care what field you're in, troubleshooting is always a pain, but once you get it to work, it feels really good. Especially if you get this to work at 3 volts. So all you need to do, yeah, I mean, right, I mean, that's, in either case, you're troubleshooting, right? I'm trying to make something work. All you got to do is create a video. Okay. Actually, it's not that bad. So you're going to create a video showing that the motor works. So basically, I need to see you in the video, your motor in the video, because I need to see how it's wired. And I just need to see your power supply too, how it's running. Okay. And this should be a short video. I'm talking like 15 to 30 seconds. Okay, because I don't need anything beyond that. And whether you put it on YouTube or whatever, the videos are going to be short enough so I can actually download them very quickly, because I had some videos in the past lives were 3 gigabytes. That took forever for me to download. Okay. In fact, in some cases, I had to ask the student to put it on YouTube because it's so slow. But regarding building it, Asher, it's not that bad to build it. Like I said, you can just sit in front of TV, watch your favorite TV program if there's anything good on now, and just build it while you're sitting there, or at least wrapping wire. Okay, of course you're going to need a hammer, right, to put to hammer the nails in. You've also been given the electrical tape in your kit, so you can tape things down. And remember that the wire has an enamel coating, so that when you make electrical connections, you actually have to use sandpaper, which we also included, to sand the ends of the wire down so that you can make the electrical connections. Because if you don't sand the wires down, it ain't going to work. Okay. If you run too much current for a long time in your motor, you might melt the enamel. Okay, and then you actually have to start from scratch. So maybe a good voltage to start at might be 6 volts. If you're concerned about how it's going to work, you might want to start at 6 volts. So I want to show you the electric motor, at least a close-up view this time. Let's compare what I showed you before. What I want to illustrate to you is the split commutator right there. You can see, and this is where the current reverses direction. And you want to make sure that the current reverses, when you build this, you want to make sure that the current reverses direction when the torque on the loop is 0. You do not want to reverse the direction of the current when the torque is maximized. So I want you to think about that. Okay? Because that's another problem students have. I had one semester, student couldn't get it to work. He was like thinking he was going to fail or whatever on the project. And I just told him one thing, and it worked like at 2 volts right away. So there's a lot of little things you can do to make this thing work well. Like I said, I have a discussion board with troubleshooting items that you can look at. One of the other things too that I've tried in the past, and we might not be able to do it this semester unless you have your own multimeter. Some multimeters measure inductance, and if you wired your armature right, your inductance will be non-zero. Will be in the millihenries. And so that's another way to test if things are wired correctly. So let me put this back together. So here, this is a brush. This is the other brush. This is our commutator. But this is for a DC motor. I gotta make sure I'm making good contact. And there's our armature. And that's my electromagnet right here. So I'm gonna run it. I'm gonna give it a kickstart. It's running at 4 volts. And look, this is much heavier. This armature is much heavier than what you have. And this is running at 4 volts. And I can kick it up to 5. And I'll go a little faster. It might go a little bit too fast. So you're basically building a version of this. Okay, I don't want it to go too fast. Now, here's the difference though. I cheated. I actually cheated in this motor. What do you think I did to cheat? You're not allowed to do this in your motor. This is the power. So I hook up the motor to the electromagnet to the power supply here, and then I hooked up the armature to the power supply here. It's the same power supply. What did I do that's not really legal? Yeah, it's in parallel. Well, that's why I'm able to run at 4 volts. Okay, it would be a little bit higher if I had in series. The reason why I did it in parallel because I can within minutes I can hook it up very quickly. Things are easier to hook up in parallel than series. I mean, I can do it in series too, but yeah, I don't know if it'd be 8 volts. I'd have to think about that. I'd say it'd be close to 8 volts. Now, your motors are going to be smaller, a lot smaller. You have a lot less weight than this thing. So I should try it. I should see what the difference is when I hook it up in series. I usually don't because this is faster for me. Okay. Any questions on this? Oh yeah. Before I go on, so when we grade this, or when I grade this, let me go back to the document. When I grade this, so it's the voltage that you run it at will earn you up to about 30 points. Okay. I'll get to your question in a minute, Patrick. And then the last 10 points comes from you answering these questions. So you got to turn this in. At least if you turn this page in, that's fine. So you just got to turn the page with answers on it. So each one of those questions is worth 2 points. So 30 points for the video showing me that the motor runs at whatever voltage it runs at. Okay. Yeah, I got to think, Patrick, I got to think of what is the resistance of the electromagnet and what is the resistance of the armature. But that's assuming that they're equal, right? If they're not equal, then I have to think about it. Oh, yeah, but you're right. If they were equal, then yeah, it would be the same as 8 volts. Actually, it'd be more than 8 volts, right? Because when they're in parallel, you have half the resistance. When they're in series, you have twice the resistance. I got to think about that. I got to do the math in my head, right? Because that's a factor of 4 difference. Yeah, sometimes I got to put pen to paper, and then I can figure it out. Sometimes I have a hard time just answering it in my head. But anyway, Patrick, you're kind of on the right track. Okay, so your video along with the answers to those questions, that's all it is. So this is not really a lot of analysis in this lab, just making sure you build this thing so that it works 3 volts. And most people, I'd say most of the people will get it working under 6 volts. Okay, most of the people will get it working under 6 volts, so it's not that bad. The 3 volts, it's actually hard, a little bit harder at 2 volts. However, when we do it in class, when we do it on campus, you can come to the lab, and I will help you. I'm able to help you with the power supply to make modifications so that this runs at 2 volts or less. Like I showed you that one. I mean, this one that I showed you. Let me go back to the camera. No, we just, as long as it's just less than 3 volts. That's all. And I had some I had some run on one battery last semester. You can actually get them to run on one of those D batteries. So like this one ran at 1.12 volts. That's what it says on this board. Okay, so this ran at 1.12 volts. So I made it 3 volts just because of the fact that I figure it's going to be a little bit harder to do it at home. But I did have people last semester run it on one of the batteries. So if you can get it to run on two batteries or less, then it's 30 points. And the reason why I gave it a range, because some of you folks have a power supply. And it does offer a little bit of an advantage. But you have a bigger advantage if you have someone on campus to help you. Okay. So this is due November 25th. Just get started soon, because you really spend more of your time, I think, troubleshooting. You can probably build this quickly. And you can probably build it in an evening. And then the rest of the time is just troubleshooting. Just be careful in building it. Wrap things nice and carefully. I've seen some that where the wrapping was just a big ball of mess, and of course, they don't work very well. Okay. Yeah, this is, to me, I think for a lot of people, this is their fun lab. For some folks who are not engineers, it might not be their fun lab. But like I said, to me, it teaches you troubleshooting. Other questions? Or concerns? Okay. So I have about 20 minutes left, so I kind of want to start the new chapter, basically because I need to. And it's on Faraday's Law. My software is causing me all kind of problems. Hold on a second. Regarding the test corrections, I don't know how quickly I'm going to get the test corrections graded, because right now I'm trying to focus on getting the worksheets graded to help prepare you for the next exam. So it's hard for me to answer that. I'm hoping within the next couple of weeks. I also want to grade the DC circuits lab. Okay, so we'll see. If everybody got all the problems right, it won't take me very long to grade. Like the worksheet from yesterday that you guys turned in on Monday, I graded that really quickly because everybody did very well on it, which is nice. Okay, because it really wasn't a super hard worksheet. It was just making sure you can go through the calculations of setting up the integral. But when there's a lot of mistakes, that makes it harder to grade. Okay, so the last chapter in this unit is on Faraday's Law. And I think this might be the most interesting chapter in the whole course. So I got to move my electric motor, and I got to get my other demo set up real quick. Just give me a second. And then I got to change the camera. So we're going to be looking at induced voltages. So what I have here is, and it's not zero properly, sorry about that. I have a galvanometer, which is used to detect current. And that's okay if it's not zero, okay? And then I have several coils. What happens if I take a magnet like this, and I put a magnet at the end so that I can make the magnetic field bigger, and I just pass it through the coils? You notice that the meter moves. So this is connected, these are connected to the meter. This detects a current. So when I run a magnet through the coil, in fact, if I have more turns, I get a bigger deflection. Like here, I get the most deflection. Yeah, I induce some current. Okay? I'm inducing a current in the loop of wire. So there's energy there. Something's pushing the electrons through. Where does the energy come from? Now, where does the energy come from? Yeah, by me pushing it. I'm doing the work. And the electrons are being pushed through here. Well, so what's causing electrons to push through there? It means you have an electric field. So somehow, by putting the magnet into the coil, I'm creating an electric field in the wire. It turns out I don't even need the wire there. The electric field will be there if I change it, if I have a changing magnetic field. So notice that if I keep a magnet in place, nothing happens. It's only when I move the magnet something happens. Okay? And whether I bring the magnet in or I bring the coil towards the magnet, I'm going to get an induced EMF. Okay? It doesn't matter what reference frame. So the induced EMF is the induced voltage. So I get a voltage induced and I have a current going through my loop. And the size of the deflection depends on how fast I run this through, which is hard for me to do, make it go real fast. It also depends on how many coils of wire are here, how many turns. It depends on which direction I move it, because if I move it in, it deflects one way, and if I pull it out, it deflects the other way. And it depends on one more thing, which I can't demonstrate with this apparatus, but I will be able to demonstrate it on Monday. The apparatus that I needed, my signal generator is not working very well. But it also depends on the angle between the face of the coil and the magnetic field. So you want me to do this? Hold on a second. I have to put it inside, don't I? If I do it out here, the thing is, I'm not penetrating the surface of the loop. Once I penetrate the surface enclosed by the loop, that's when I get an induced voltage. So, that's a very good question, right? Because that really illustrates to you that once I'm outside the loop, nothing happens. But I have to penetrate the surface enclosed by each one of these loops. And then I get an induced EMF. But the angle, this also depends on the angle between. Oh, you want me to do it in the front? Right? I'm not penetrating the surface enclosed by the loop, am I? I'm not those are very good questions. I have to penetrate the surface. Okay. So, in fact, the angle between the surface and the magnetic field plays a role too. And I'm able to just, when I get my new signal generator, I'll be able to show you that on Monday. Okay. So Faraday made the discovery. Okay, let me change to the PowerPoint. So Faraday made the discovery. Let me leave it here for now. And of course, it's named named after Faraday. It's called Faraday's Law. And again, that a current will be induced in the loop of wire. There's a potential difference in the wire. This is what's weird. There's a potential difference in the wire, and we have a closed loop. There's something weird about this because, anytime you have a closed loop, the integral electric field around the loop is 0. Yeah, I think, Patrick, the board I was shaking. That's probably why you saw deflection. And so that voltage is induced, we call it an induced EMF. And you should have noticed that the induced current depends on the velocity of the magnet, and the direction of the current depends on which pole of the magnet is inserted first. Now, the induced EMF is the same whether the north pole of the magnet moves into the coil or the coil is moved towards the north pole of the magnet at the same speed. And this reflects the fact that all the laws of physics are the same in every reference frame. In fact, this idea, or this phenomena, was discovered by two people. One was Faraday and one was Joseph Henry. Okay, but Faraday got credit for it. So what affects the induced current? The rate at which the field changes, the area of the loop of wire exposed to the magnetic field. If you have a circuit moving in a magnetic field, that affects the induced current. Okay. But that affects the induced EMF. If you have a loop of wire running through a magnetic field, you'll get an EMF, but you won't get a current, really. And I'll show you an example of that. This idea was discovered both by, like I said, Faraday and Henry, but Faraday gets credit for it. And it's called Faraday's Law. And Faraday's Law is that the induced EMF is minus the time rate of change of the flux through the loop. Let me rephrase that. The flux through the area enclosed by the loop. And so we write it as the induced EMF we'll call it delta V. You can say delta V induced is minus d phi sub b over dt is equal to minus the time derivative of the magnetic flux dot dA. This is not something you derive. Okay, this is a it's the law that was discovered by Faraday. And this is the magnetic flux. Okay, through the surface enclosed by the loop. So if you have a loop of wire like this, we're talking about this surface. Okay, it's an open surface. It's not a closed surface like in Gauss's law. This is the flux through an open surface. So there's an ambiguity in terms of what your normal to the surface is. So maybe I should write it this way. Instead of in terms of the area vector. So there's an ambiguity in this because if you have an open surface, the normal could point out towards us or to the board in this particular case. Okay. Generally what you do is you choose the normal in the direction of the magnetic field for most problems. Okay. Or the general direction of it. We're going to be doing problems where the field is essentially uniform but time dependent. So here's an example where you actually have two circuits. This is usually something I demonstrate in class, but this requires too much equipment to bring it home. So I have a battery and a switch, and I have a wire wrapped around iron core. The idea of the iron core is to increase the magnetic field because it gets magnetized. And then on the other side, I have a secondary coil connected to a galvanometer. If I flip the switch, in the act of flipping the switch, I'm going to have a time-dependent magnetic field because I'm going to have a time-dependent current. You're going to have a change in flux through this loop. Right? You're going to have a change in flux through this loop on the right. So if I close this switch, I'll have a time-dependent current, time-dependent magnetic field. Then you're going to get a change in flux through here, and then this galvanometer will deflect. I have two separate circuits. Those two circuits are completely isolated from each other, and I still can get on the electric field that goes through here. So what does that kind of tell you about the electric field? Yeah, that's a simple transformer. The electric field is going to be there whether I have the wire or not. Okay, the electric field is going to be there whether I have the wire there or not. Okay, I want to do this example in class. I want to wait till class for this example. So the question is, what force is causing a charge to move in the wire? It's not a magnetic force because it can't do work on a charged particle, but it's really an electric field that's induced. Somehow a field is created as the flux changes, and the work putting a charge done by this field is the integral of the electric field around the loop, and that's the induced EMF. So if I integrate the electric field around a loop, let's say this loop, that's going to be the induced EMF. This is the field that's induced. This has the same properties of the magnetic field. Magnetic fields form closed loops. This electric field forms closed loops too. It's a non-conservative field. Because when we learn from Kirchhoff's laws, the integral of the electric field around the closed loop is 0. That's not the case here. Okay, that's not the case here. So the induced EMF can be written as an integral of the electric field around the loop. Now, that electric field exists whether or not the loop is there. All the loop does is provide a path for the electrons to move around. Okay? So you take a loop of wire, you put it in that field, the electrons are going to feel a force, and they're going to move in that loop. So again, I'm going to not do this example until Monday. I just want to talk about the concepts. Let me just say a couple of things about the properties of this field, and I'm going to stop. What are the properties of this induced electric field? No charges are required to create it. It's mathematically described as a divergences, just like the magnetic field. It has the same properties as the magnetic field. And it has to because it comes from the magnetic field. It comes from the fact that the magnetic field is changing. These field lines form closed loop. They circulate around the source just like the magnetic field. They do require a time-varying magnetic field, and no physical circuit is required. Again, the loop only provides a path for electrons to move through it. And so in the case where the magnetic field depends on time, the induced electric field is present even in the absence of any circuit. So I'm going to stop here, and then I will, on Monday, I'll probably start off, I'll probably review a little bit, and then go through a couple of the examples. And so by Monday, I will have covered most of the chapter. Okay? All right, so I'm going to need to end it here. You're welcome. And we will see you on, well, I might see you in problem solving. If I don't see you in problem solving, see you on Monday. See you.